And I'm going to show you how to do these analyses two different ways. I'm going to show you what we do if we treat treatment or concentration of oil as a categorical variable. And then I'm also going to show you what we do if we treat it as a numeric variable, because it really can be both in this case. Then the other two variables are trial number. We're not really going to use that variable much. And then we have this GIZ in centimeters. That's growth inhibition zone measured in centimeters. So looking at the graph, if we've got the concentration of oil as a treatment variable, this is the analysis we're going to do. So I plot growth inhibition zone. We see one data point for every measurement. And then I'm going to add concentration of oil, and we split that up. And now what you see here is called a jittered dot plot, where each of these dots is sort of clustered above all of those categories that are on X. And now remember, our categories happen to be numbers, right? We've got 0, 20, 40, 60, 80, 100, but we're treating them as if they're categories. They could be red, yellow, blue, green. We're treating them as categories. And this will give us the ability to add descriptive statistics here. And we're looking at mean and 95% confidence interval. But I'm going to show these means as bars. And I'm going to make those bars much wider than the default. I want to say with this graph, the kind of the question that the student is asking is, does the GIZ differ by treatment, right? Does it differ by this treatment, this concentration of oil treatment? And I think the answer is a resounding yes here. It does. If I want to apply statistics, I'm going to pop open the graph-driven hypothesis test. And this is going to be an ANOVA analysis. This is the analysis of variance. Student will get a pop-up that says, we're testing for a difference in the average value of a numeric variable between 3 or more different groups. In this case, we have 6 groups. And this is what we're doing. We can calculate it. We get a very low probability value, less than 0.01, extremely strong confidence the groups are different. We can run the post hoc test to compare the pairwise comparisons. You see basically every group is significantly different from one another, except for the 80% to 60 group. They are not significantly different from one another. And you can see that in the post hoc test. The other thing I'll say is that's an awful lot of post hoc tests for not a huge amount of data. So you can take those post hoc tests with a grain of salt. But the overall result that oil concentration seems to affect GIZ, that seems to be a pretty ironclad result, and the stats back that up. Now, the next thing I want to show you is if we I'm going to go ahead and treat concentration of oil as a numeric variable. And I'm going to change concentration of oil. I'm getting this little drop down underneath the variable, and I'm going to make it be numeric. And I'm going to put it back on the plot. And this gives me a really weird graph because I don't want to show means as bars again. So I'm going to go back into the appearance menu, and I'm going to go back to showing means as a dot. That is showing us the mean and 95% confidence interval at each of those numeric levels along there. And again, the computer is recognizing that we had groups, and it's giving us the mean of the 60% oil concentration as one, the mean of the 80% as a second. And then that line of best fit, we've added a linear regression line. And this is a different hypothesis to test. So before, when we were looking at the bars and we were treating concentration of oil as categories, that was saying, does the mean of GIZ differ across my categories? Now this is treating both X and Y as numbers, and it's saying, is there a numeric relationship between concentration of oil and GIZ? Or in other words, is the slope significantly different from 0? And so it's testing if the slope is significantly different from 0. And so if we run the hypothesis test, it's going to say linear regression. We're no longer doing ANOVA. It's going to say, hey, this is the test you want to use to test for a relationship between two numbers or two groups of numbers. And when you calculate it, it's going to give us a probability value. And again, this is significant. It's less than 0.01, but it's saying the chance of getting a slope like this due to random chance alone is less than 1%, where the last test was saying the chance of getting means that were this different from one another is less than 1%. It's a subtle difference, but it's just kind of because it's doing different math, it's telling you something slightly different. Both of those ways that I just showed you, I think are perfectly fine. I think they're justifiable by a student. If a student explained like, hey, I did this, I did the first way because I was testing for a difference in the average between my different treatment groups. Or they could say, oh, I did it this way because I was testing for a relationship between the value of concentration of oil and the value of GIZ. Both of those are correct. That's one of the things I think is often, maddening about learning statistics is there isn't one right answer.